Welcome to Math 2210. We'll be doing some problems from Chapter 10. First situation is we'll be comparing two population means where sigma, the population standard deviation, is unknown. Now the book does some problems where it assumes that sigma is known, but in fact, in real life, if you don't know what the population means are, how would you possibly know what the population standard deviation is? So really, in realistic problems, sigma is always unknown. All right, suppose a noted scientist claims that the average weight of R4 droids is equal to the average weight of R2 droids. Here, let's just quickly write down our null hypothesis. So we're saying here that the average weights are equal. So we could have the average weight of the R4s is equal to the average weight of the R2s. That bar means mean or an average. All right, now we believe that the R2 droids have a larger average weight. So our alternative hypothesis, which is what we're always trying to prove with the data, we're always trying to prove the alternative. There, we would, let's go back and read it. We believe that the R2 droids have a larger average weight, so it would look like that. Remember, the equal sign is always in the null hypothesis. The alternative is always greater than, less than, or not equal to. All right, so let's look at the data here on these two populations. First of all, for the R4s, we have a sample of 16. We have a mean weight for these, for the sample of 75, standard deviation 3.2. For the R2s, we have fewer of them. We have 13. We have the weight, average weight is equal to 79, and standard deviation, could just use S also, is 6.5. We want to test at the 5% level of significance, so this means that alpha equals 0.05. Now before we reach for the calculator, let's just look at this. If you wanted to trust this sample, and if you had no reason to doubt it, then it does look like the R2 units are heavier. Average weight is 79 kilograms versus 75. But we know that when we take random samples, that there's always a chance, just by the luck of the draw, that these samples may not really be representative. So that's why we do hypothesis testing. Just because a sample says that one group is heavier doesn't really tell you with 100% accuracy that the entire population would also go that way. All right, recommend you might want to pause, jot down these numbers, and I will switch to the calculator here. All right, let me find it. Okay, there we are. Okay, that's, I'm sure it'll be no surprise to you. I already clicked stat, and we're going to go to test. We're doing a hypothesis test. Now, we were comparing two population means here. So let's go down. This is a two-sample t-test that you'll do to compare means. We'll do an example later with proportions, but means two-sample t-test. All right, let's enter that. And we have stats rather than data here. Great. And notice how easy it is to put these figures in. We will put in a mean, a sample standard deviation, and then n. All right, so for the first one, recall that the mean was 75. Standard deviation was 3.2. And then n was 16. For the next one, it was 79 and 6.5. and 13. Now we are trying to show that the first set is smaller than the second set. So mu1 is less than mu2. Enter there. Next it says pooled or not. That has no significance to the stuff we'll be learning in this class, so it will be no. And let's just go ahead and calculate it, see what we've got. Now, you know, it gives you some values if you've read the book. You know, essentially the theory behind this uses DF, degrees of freedom, and T values and that. But to make your conclusion, all you really need to do is look at that p-value. We have a p-value, the third one down here, of 0.02, just about 0.03. So as p is 0.03, remember the phrase I taught you? If p is low, then h null must go. So in other words, you would reject the null hypothesis. Well, how small does p have to be? It has to be smaller than the alpha. We wanted to test this at the 5% level of significance, that is 0.05, and p here is less than that 0.05. So we reject the null hypothesis, and we accept the alternative hypothesis, which is that yes, the average weight of the R4 droids is less than the average weight of the R2 droids. Now, we could be wrong. There's always a chance that we're wrong. And the p-value essentially tells you the probability you could be wrong. We have about a 3% chance of incorrectly rejecting the null hypothesis. That's why in really important things you may want a very small p-value. I know the book says generally 0.05 is used, but sometimes smaller or larger values are used. All right, let's go back to the PowerPoint and we'll go to the next slide. This time, instead of comparing two means, we're going to compare two independent population proportions. All right, fans of the Princess Bride, a survey reveals that 9 out of 12 Gilderites believe that Princess Buttercup should marry Prince Humperdinck, while 13 out of 21 Florinites are in favor. Is the proportion of Gilderites in favor of the marriage greater than the proportion of the Florinites? Test at this case 10%, so alpha equals 0.1 level of significance. Now, you know your alternative hypothesis. Remember, your alternative hypothesis is always what you're trying to prove. That question there near the end is a proportion of Gilderites. So proportion is a proportion of the Gilderites greater than the proportion of the Florinites. P hat represents a proportion. When you look at the readout later, you don't want to confuse this with P, your probability value. All right, so the data here is real easy. Jot it down. We can go to the calculator right away for this problem. And so let's see what we're going to select here. I'll quit this. And under stat, of course, I am doing a hypothesis test. Now, we have in our data two different proportions. So you can probably guess where I'm going to go here. It's going to be number 6, our 2 proportion. It is a z-test. There's some theory in the book as to why that's the case, but to do the problem, you just need to know 2 proportion z-test. And let's enter that. Look how easy it is to put in the data for this problem. All right, so for the Gilderites, I had 9 out of 6. Oh, is this the right data? Almost looks like oh, okay, never mind. 9 out of 12. For a minute there, I was thinking, did I already put this in here? Okay, we had 9 out of 12 for the Gilderites, and then we had 13 out of 21. So there we go. And we were trying to prove that the first proportion is greater than the second proportion, so P1 is greater than P2. Go over, sorry, let me find it here. Okay, there we are. Click enter so that it switches to that. I've had some emails from people, I think they forgot to click the enter. There, now we've entered and we're doing P1 greater than P2. I'm doing a lot of talking here, but notice, and in fact, it's a very quick problem to do. So let's see what we have. P equals, and I'm talking about this P here, it's 0.22. If P is low, then H0 or H null must go. But P is not very low here. I can't imagine I've never seen a case where people did a hypothesis test where they were okay with such a large value of P. We said alpha is 0.10 and P is certainly not smaller than that. So we cannot reject the null hypothesis. In other words, at this point, would assume that they're equal to each other. Now notice that P hat of 1 and P hat 2, P hat 1 is certainly bigger than the second one. Okay, it's just based on probably the fact that we have fairly small sample sizes here, that if we were to conclude the alternative hypothesis and say, well, this is greater than this, we'd have a 22% chance of being wrong. And generally speaking, that's just too high a chance of being wrong. Occasionally I've seen that alpha equals 0.10, but I've never seen a case where people used a larger alpha than that. Now we have one more example we're going to do in this lesson here. And let me get to it here. The last one, I'm going to show you how you can compare matched or paired samples. Classic case here would be like a before and after situation. You have something, you take a measurement, you do some experiment or you manipulate it in some way, and then you go back and take another measurement on it. Or it could be that you look at something like now and then you look at it again 10 years from now. You know? So before or after is the most typical situation. And you see here, Professor Luoma claims that members of his Use It and Lose It fitness center will lose weight in the first month. Test the following data at the 5% significance level. So notice in the data here I have 7 different members of my fitness center. I have the weight at the start in pounds and then the weight after a month in pounds. And I'm claiming that they will lose weight. Okay. Can you figure out what the alternative hypothesis is? Well, I'm claiming that they will lose weight, right? So I'm just going to put it in words here. I'm going to claim that the weight loss is greater than 0. Now H null, the null hypothesis, I suppose, would just be that the weight loss equals 0. Okay? Really, the alternate is a really important one because that's the one that we are trying to prove. All right, now before I go and reach for the calculator, a little bit of preliminary work I want to do. When we're doing this, what we're actually going to work out is we are going to take our starting weight and we are going to subtract our weight after a month. See what happens. Now notice if we did 191 minus 186, that would equal a 5 pounds in weight loss, which that line certainly does support a weight loss being greater than 0, doesn't it? Now if you scrutinize this, you might see that there's, for instance, in our last data line there, person comes in at 183, leaves at 184, that's a -1. That's actually a weight gain in this case. A negative weight loss is a weight gain. Well, when we do a test, we're not actually going to enter both of these columns. We're going to do a test based on these figures here. Now there's several ways you could do it. You could just using paper and pencil do the rest of these subtractions, and get this last column here, and then you could go and in stat under the enter, actually it's under edit, you could create an L1 column like you've done on many other problems. The author also shows you that you can do some programming in your calculator to accomplish this. I find most of my students have never done programming in the calculator, so I'd rather kind of avoid that. If you know how to do it and you watch the author video, it's not that tough. But I'm going to show you a neat little way where when you're creating the list, you can have it do this math for you. All right, so this will be our last visit to the calculator in this lesson. I'll go to stat. Okay, now we're going to have to enter a list, so yes, we're going to do edit here. And here's how you can do it. Okay, if again, you'll be using this data from that chart. The first line had 191 and 186. Well, you can actually do the calculation here. You can do 191 minus 186, enter, and that's the 5 that we worked out a couple minutes ago. And then I'll just continue. The next line is 245 minus 224. Okay, that tells us we had a 21 there. And then 167 minus 172. There the person gained 5 pounds, so the weight loss is negative. All right, next one, 307 minus 299. And then 194 minus 194. Well, I knew what that one would be before I typed it in. 206 minus 197, and on my last one, 183 minus 184. Okay, so those were our 7 data points. I'll quit this. I'll go to stat. Now you see we only have one column of data now that we just created by subtracting those. So the neat thing is you can go back to something you've used several chapters ago. You can just use your t-test. And so I will do that. I'm going to enter data because I need to enter that L1 column. So data. And in this case, the first thing, we're going to assume that the mean weight loss is 0. In other words, my fitness place didn't accomplish anything. Sure, we're going to use L1, frequency 1. That just meant that each of those data points represented one person. And now what are we trying to show? Well, I wanted to show that the average was greater than 0. The correct one is already highlighted. And I'll go down to calculate and let's see what interesting things we find out. Well, at the 5% significance level, I can't reject the null hypothesis because this is just about 0.08%. So if I'd used a lower standard, such as alpha equals 10%, then I'd say, yeah, I can reject the null hypothesis, but not if I want to stick with a 5% significance level. Notice that X bar is about 5 pounds. So based on the sample, people did lose about 5 pounds. It's just we didn't have very much data and we don't want to really accept the alternate hypothesis at this point. So what might we do? Well, perhaps we go and collect data on more members. If we do that, get a little more data, perhaps we really could go and reject the null hypothesis. So at this point, I don't really have proof that this use it and lose it fitness center can brag about weight loss. By the way, just last comment here, a little practical thing, because a number of you, I'm sure, will be doing some hypothesis testing for other classes. It's become rather fashionable to not even give a level of alpha and just state the p-value in studies. So they'll just tell you, okay, the p-value equals 0.077. That way the reader can decide whether he or she wants this to be good enough. As I said, 0.05 is fairly standard. Sometimes people will let alpha equal 0.10, so they'll just give the p-value and let you make up your own mind. All right, folks, well, that's it. Good luck. I think you should do fine with the homework problems.